Okay, all right. So today we have Andre Wibisono as our speaker. He's faculty at Yale University, and he has joined us from the Department of Computer Science and also Department of Statistics and Data Science. So he's been doing research in optimization and sampling, and then he has many beautiful results like analyzing continuous time dynamic and also very neat technique in discretization. And he has a MSS career award. Before starting as the faculty at Yale, he was a postdoc at Georgia Tech, and that's when and where I met Andre. And then after I get on my PhD, I become postdoc of Andre. And then he's very good for me. So I'm also very happy to have him here today. And so maybe let's start with some applause.
Well, thank you, Junken, for the kind introduction. Thanks, everyone. Hopefully, I can live up to the applause. Thanks for having me, and thanks for attending this talk. It's my first time in the San Diego campus, so it's nice and sunny here. So today I will give a synthesis of a few works, and the theme will be the title will be survey on the mixing time of the proximal sampler algorithm. I'll try to illustrate what is this algorithm that I think is a newer, interesting kind of sampling algorithm. And so this will be from a sequence of joint works with my colleague Santosh Vempala at Georgia Tech, Yongshin Chen at Georgia Tech, Sinho Chui at Yale, and Adil Salim at Microsoft. Let me try to give a brief overview of just to set the context of what happens for sampling in continuous time via what's called Langevin dynamics. And then the main part of the talk will be this proximal sampler on the third part. And if we have time, I'll try to say a few words about the proof techniques. Okay, so in this talk, we care about a sampling problem. So the goal is to draw a sample from some target distribution that I'll denote by nu here. And for today's talk, assume that the target distribution has full support. Suppose that we know the density function up to some normalizing constant that we don't know. And so let me write the density as exponential of negative f. And let me assume for today that this f is differentiable or twice differentiable. Just for simplicity, there are other things we can do if f is not differentiable. And here we don't know this normalizing constant, and we don't need to know that. But assume for now that we know how to evaluate f and also the gradient of f. So the first order oracle setting. And sampling has many applications. For example, in Bayesian inference, often we have some nice generative model with nice prior, nice likelihood, but even in the nicer setting, the posterior distribution is usually not in the same class. And then we cannot represent that exactly. And then one way to get around that is to draw samples from this posterior and use the statistics of the sample as an approximate posterior. But sampling also comes up in a lot of applications for numerical integration, uncertainty quantification, privacy, and so on. And I think what's also interesting about sampling is that it has very deep connection to optimization. Usually either minimizing f, or in this talk, it will be about optimization but on the space of probability distributions. So to be more concrete, in continuous time, turns out like a very good dynamics to sample from this target distribution nu is what's called Langevin dynamics. So it is a stochastic process on the state space, Euclidean space. So xt is my random variable moving over time. And the evolution of my random variable is governed by, there is a drift term that has to do with this is the score function of my target. And then I add Brownian motion. So without the Brownian motion component, this will just be gradient flow to minimize f, my potential function. But that turns out that if we add this Brownian motion with this very specific scaling √2, that turns out this becomes a very nice dynamics to sample from this target e to the negative f. So I think for me, that's a very magical thing. And turns out there is a very nice, simple way to understand that via this optimization perspective. And what I will try to illustrate today also is that under some assumption on the target distribution, for example, when the target is strongly log-concave, say looks like a Gaussian like this, so unimodal and has fast tail decay, or if the target has some what's called isoperimetry inequality, for example, log Sobolev or Poincaré and so on. So the target can be non-log concave, can be multimodal, but not too bad. Then turns out that under these kind of assumptions, we can say very strong guarantees on how fast these stochastic processes are converging, right? And then the main interest into this talk will be what can we say in discrete time when we want to actually implement these as concrete algorithms. But to get there, how do we understand stochastic process like this? Turns out that there is this mechanical translation you can do that says that if your process evolves following this Langevin dynamics, then the density function rho t. So this will be a density function on the state space. So this is a map from state space to real that integrates to 1. The statement is that if xt evolves following Langevin dynamics, then the density function evolves following a PDE called Fokker-Planck equation that looks like this. So at every state space x, the time derivative of my density is given by the divergence of my density times my drift term here, plus this Laplacian that comes from the Brownian motion component. And then turns out there is this mathematical identity that says that we can write this more concisely as the divergence of my target, of my iterate, times the gradient log relative density of my iterate at the target distribution. So then this is where we see more explicitly the dependence on the target. And from here, we can also see that if my iterate is at the same at the target, then this whole right-hand side will be 0 and I don't move. So the target is stationary. But more than that, turns out that the target is an attracting fixed point. And turns out that also that this PDE, this Fokker-Planck equation, can be seen as the gradient flow dynamics for minimizing some objective function, namely relative entropy or KL divergence. But the gradient flow is happening in the space of probability distribution with the metric given by the W2 metric, the Wasserstein metric induced by optimal transport. And this was the beautiful result by this classical paper by Jordan, Kinderlehrer, and Otto from 98, JKO. And then this will be the starting point of what we will discuss here. So in particular, this optimization perspective says that we can in fact view sampling as optimizing in the space of distributions. And so concretely, in sampling, we want to draw a sample from some target distribution. Let's convert that to optimizing some objective function, say KL divergence, on the space of distribution. So I'm operating on the top space here. In principle, my objective function can be anything that's minimized at my target distribution. But turns out that KL divergence is a very nice objective function. For example, if we run the gradient flow dynamics to minimize KL divergence on the space of distribution, what we get is exactly the PDE for Fokker-Planck equation. And then how to realize a PDE is we can simulate the Langevin dynamics, which is happening on the state space. And so there is this translation that we start from an objective function on the space distribution. We run some optimization algorithm there. We get some PDE, some dynamics on the space distribution. And then the goal is to realize that dynamics, that algorithm, as something that we can simulate only via samples. So in this figure, xk will be a sample from this distribution rho k, and xk plus 1 will be one step of the random walk from xk. And we want to design this random walk such that how the distribution changes from xk to xk plus 1 is exactly what we want to simulate at the level of distribution. So if the dynamics at the level of distribution is the Fokker-Planck equation, then we can do that via Langevin dynamics, which is the gradient flow to minimize KL divergence. And the proximal sampler, what I will discuss today, can be seen as some proximal discretization of the Langevin dynamics. And in this correspondence, in today's talk, I will choose my objective function to be KL divergence, relative entropy. So the relative entropy between my distribution rho and my target nu is this expected log relative density expectation over my current distribution. The metric on the space of distribution is given by the Wasserstein distance, which is induced by optimal transport. And turns out that if we choose this objective function with this metric, then if you compute the squared gradient norm of this objective function, that gives us what's called Fisher information, the relative Fisher information between my two distributions, which is given by the expectation of the difference of the score function of the two distribution. Right? So KL divergence is measuring the difference of the log density. Relative Fisher information is measuring the difference of the score function, the gradient of the log density. Right? And then this will come up in the convergence guarantees. So and here's the definition of what I mentioned previously. So and these are classical definitions. So we say that a target distribution nu is strongly log concave if f, the negative log density, is a strongly convex function. Say the second derivative, the Hessian matrix, is always strictly positive. So the distribution has to look unimodal and log concave and like a Gaussian, basically, right? On the other hand, we say that a target distribution nu satisfies log Sobolev inequality, LSI, with some constant alpha, if for any other distribution rho, my relative Fisher information is an upper bound to my KL divergence. So it turns out that these two definitions have very nice optimization meaning. Again, here we are looking at the space of distribution with the Wasserstein metric. So it turns out that saying that a distribution is only log concave is equivalent to saying that my objective function f, which is KL divergence, is a strongly convex function on this manifold of distribution. Say the Hessian matrix, the Hessian operator is strictly positive. And similarly, saying that a target distribution nu satisfies log Sobolev turns out to be the same as saying that my objective function KL divergence satisfies this alpha PL condition, the alpha Polyak-Lojasiewicz condition from optimization. And the general definition of this PL condition is saying that my gradient norm squared is an upper bound to my function gap, my function value minus the minimum value. For us, this f is the KL divergence, the minimum value is 0, so the right-hand side is exactly this one. And the left-hand side, the squared norm of gradient of KL divergence is exactly the Fisher information. So it turns out that log Sobolev, which is a classical definition from functional analysis and measure theory and so on, has a really nice optimization meaning. And from optimization, we know that PL condition is sufficient to get fast convergence for optimization, right? And also what's nice is that strong log-concavity implies log Sobolev. This is a classical result by Bakley-Emery. Also from optimization, we know that strong convexity implies PL condition. But what's nice about sampling that goes a little bit beyond the standard optimization is that this condition, this isoperimetry condition, log Sobolev, is stable under some operations. For example, it's stable if we perturb the density function. That's what's called the Hardy-Stroke perturbation lemma. Or it's stable if we map the state space by a Lipschitz map. So stable under this Lipschitz push forward. So what that means is that we can take a nice distribution, satisfies strong log concavity like a Gaussian. Then we can perturb the density function a little bit to get something that's not log concave, but still satisfies log Sobolev. Right? So the right-hand side here is not log concave. If we try to optimize the negative log density of this objective function of this distribution on the right-hand side, we will get stuck at all the local minima here. Right? But if we try to sample from this, turns out that we can still sample efficiently.
Is that what it actually looks like in 1D?
This is an example of a distribution of the log Sobolev, yeah.
Okay, so it means it's literally bounded above by a Gaussian, like that.
Oh, it doesn't have to be a, you can, the perturbation you can go up. Yeah, as long as I don't say if you perturb the distribution, your log Sobolev constant will degrade and the degradation will be exponentially bad in the size of the perturbation, but it will still satisfy some positive log Sobolev constant. So for example, and also in my convention here, bigger log Sobolev constant is better. So what you can show, for example, what is known is that mixture of two Gaussian and a mixture of Gaussian will satisfy log Sobolev, but the constant will be exponentially bad in the size of the separation of the modes. So that in principle, we can sample from this mixture of Gaussian, but the rate will be very slow. But here, if I'm perturbing by just a little bit, then this constant, my log Sobolev constant will still be on the order of 1. Does that answer your question?
So if nu is a 1D density.
Yeah.
Yeah, so X is in R1. Does the log Sobolev condition reduce to being bounded above by a Gaussian, like a bell curve, like in the illustration?
Not necessarily.
What's the illustration mean in the right column at the top?
This supposed to illustrate that I can take something that's nice like a Gaussian. I can perturb the density function to get something that's not log concave. The perturbation, it can go up beyond the Gaussian.
Okay.
Yeah. So the upper bound doesn't give much information.
Should I interpret the right column literally or just illustratively?
Is in illustration to say that the class of distributions satisfying log Sobolev is larger than log concave distribution. You can have multiple modes. But log Sobolev has to do more with the tail decay. Your tail has to decay sub-Gaussian, like a sub-Gaussian tail, for example. Like a Poincare inequality is weaker than this. I don't have the illustration, but your tail can be sub-exponential. Yeah. Thanks for the question. So here's a review of what's known about convergence guarantee. So if the target is strongly log concave, like the left-hand side here, then along the continuous time Langevin dynamics, I can say very strong guarantees for the convergence rate. So for example, the W2 distance, the distance between my two iterates will contract exponentially fast. So in particular, the distance between my iterate and the target will be decaying exponentially fast in time. Under log Sobolev, which is weaker, we don't have the exponential contraction in the distance, but we can say that the objective value, my KL divergence, is decreasing exponentially fast with time. On the other hand, under strong log-concavity, from optimization, we know that if we try to minimize a strongly convex objective function along gradient flow, we can show that the squared norm of the gradient is decreasing exponentially fast. For sampling, that becomes a statement that the visual information between my iterate and the target is decaying exponentially fast in time. So far, this is still a class from classical optimization, but then there is something again in sampling that goes beyond optimization. So for example, on the log Sobolev, turns out that we have exponential convergence, not just in KL divergence, but also in all this family of what's called Rényi divergence. So here's a reminder of the Rényi divergence of order Q bigger than 1 between two distributions is this definition here. KL divergence is a limit when the index Q is equal to 1. And in general, this Rényi divergence is getting larger as you increase the index. So Rényi divergence order Q is a stronger guarantee than KL divergence. And what's nice is that this log Sobolev, which is the PL condition for KL divergence, turns out to be strong enough to show that Rényi divergence is also decaying exponentially fast. And the rate only decays by this 1/Q, the index of the Rényi divergence. And Rényi divergence has a lot of other applications also in privacy and so on. So okay, so this is a review of what happens in continuous time. And now the interest will be understanding what can we say in discrete time when we approximate this continuous time process by some discrete time updates, and which one of these guarantees can still survive in discrete time. And to do that, let me briefly recall that in optimization, in continuous time, this is the classical gradient flow dynamics, first order dynamics, a greedy dynamics along negative gradient of my objective function. I can discretize this dynamics in many different ways. For example, if I discretize gradient flow in a forward way, in an explicit way, I get what's called gradient descent algorithm, say with step size eta here. Right? This is a simple explicit update where in every iteration, I'm at my current iterate xk, and then I just take a step along my negative gradient, my current iterate. On the other hand, if I discretize in the backward way, I get this proximal gradient method, where the update from my current iterate xk, I want to take a step along the negative gradient of my next iterate xk plus 1. So then this becomes an implicit equation But then from our optimization, we know that turns out one way to solve this is to say that in every iteration, we want to minimize this regularized objective function. We want to minimize f, the true objective, plus this quadratic regularization centered at my current iterate. Right? And we know that both of these have convergence guarantees. Usually for green descent, we need smoothness. For proximal, we get better convergence as long as we can implement this implicit update here. Right? So for sampling, what is the corresponding picture here? In continuous time, we look at Langevin dynamics. I'm writing down the stochastic process representation, but really the PDE version of this one is the gradient flow to minimize KL divergence. I will mention a few words about what's called the unadjusted Langevin algorithm, ULA, which is this very explicit algorithm that's very much used in practice. Turns out this explicit algorithm has an asymptotic bias issue. And then I will spend more time talking about this other discretization called the proximal sampler, and I'll try to illustrate what this symbol means. And turns out this is unbiased, and we can show really nice convergence rate guarantees matching continuous time. Oh, yeah.
Just want to make sure I understand the previous slide, talk about proximal gradient.
Yeah.
So this looks to me the proximal point.
Yes. So this
Proximal gradient. You know, when we typically talk about proximal gradient, there's a regularizer, a smooth regularizer.
Yeah.
That you have this two-step thing.
Yes.
So this is proximal
Yeah.
point.
Correct. Yeah. Thank you. Yeah. I should call it proximal point method. Yeah. Thank you. Yeah. Usually proximal gradient refers to this for composite objective function. Yeah. Sorry. Like the proximal. I say gradient here to match with the gradient.
So you're not going to be dealing with non-smooth regularizers on the sampling objective.
No, I will not. But I will have a slide about the composite objective, composite optimization that addresses something like that. Yeah. But thank you. Yeah.
So I have a quick question on the next slide. So the objective is to sample from e to the minus f.
Yes.
And the second step of the proximal sampler, you're saying the next iterative sample from e to the minus f plus something. So if we don't know e to the minus f, how do we sample from?
I will talk about that here. The answer will be that assume for now we can evaluate f and the gradient.
Okay.
Then it's like here we want to sample from this regularized distribution. It turns out that one way to do that is via rejection sampling. Turns out that if we choose a step size small enough, then this becomes a very nice, well-conditioned distribution, and we can use rejection sampling to sample with constant number of iteration. The same principle as for optimization. How do we optimize this? If we assume that f is smooth and the step size is small, then this becomes a very strongly convex and smooth objective with constant condition number, and then we can run any other algorithm. So for sampling, rejection sampling is a good way to do that. Yeah. But I can talk about that more. Thank you for the questions. Okay, let me mention this quickly maybe. So so the first level question is we want to match this figure between optimization and sampling, right? So the right-hand side is we want to sample in continuous time. We have Langevin dynamics, and suppose for now I care about log Sobolev. So I know that I get this convergence rate in KL divergence. The optimization meaning of this one is that if we minimize an objective function f, here f will be KL divergence. If we have PL condition, then we get this exponential convergence rate in function value. In discrete time, if we discretize, then assuming we have smoothness and step size not too large, then we know that gradient descent also has exponential convergence rate. Right? The question is, can we show that for sampling? And well, the first question is, what is the algorithm? And typically, this is the simple algorithm that people use. A lot of people use in practice. What's called unadjusted Langevin algorithm. So the algorithm looks like from now my current iterate xk will be a random variable. I take a gradient step along my negative gradient of f. F is my negative log density. And then I add Gaussian noise, independent Gaussian noise with this very specific scaling here. 8 times my step size. And here I'm multiplying my Gaussian with square root 2 eta. And why are we doing this? Because so that we can say that in the limit as step size going to 0, this recovers exactly the continuous time Langevin dynamics. But the issue here is that if you choose the step size eta to be non-zero, positive, no matter how small, but suppose you keep it fixed over iteration, then if you keep running this update, this is a Markov chain, right? From xk, you go to a random xk plus 1. In the limit as iteration goes to infinity, your iterate will converge in distribution to some limiting stationary distribution that we call this new sub eta. And it turns out that this limiting distribution will not be the same as my original target, e to the negative f, no matter how small this step size is. And this is present even if your target is the nicest possible thing, say Gaussian with mean 0 and some isotropic covariance. Then you can solve this update explicitly, and you can check that the limiting distribution, nu eta, is also Gaussian. The mean is correct, but the covariance gets a bit too large by something, a factor that has to do with step size. So, so the bias you can control to be small, but the issue is that if we want to derive the number of iteration to reach a specific target accuracy, then it will give us a bad dependence. Right. So, for example, since about 10 years ago, there has been a lot of work understanding the non-asymptotic convergence guarantees of this algorithm, starting from the work of Dalalian and then Durmu and Mullins and so on. Typically assuming that the potential F is convex, sorry, convex and smooth, so that we can do coupling techniques. I will show you guarantee under log Sobolev. Let me say that in practice, this bias issue is typically not a real obstruction in practice. In practice, typically, you run a Markov chain and then you add what's called a metropolis filter, an accept-reject step. And the effect of this metropolis filter is that it always removes the bias. It forces your Markov chain, this combined Markov chain, to be stationary, to be reversible with respect to your target distribution. So if your Markov chain is ULA, if you add metropolis filter, this is called MALA, metropolis adjusted Langevin algorithm. Also, this is why ULA is called unadjusted, right? So if you remove the bias, you can show high accuracy guarantee. But at least from the technical side, one difficulty is that the proof technique becomes a bit more complicated. You can show guarantees only in weaker metrics, and it loses this connection to optimization. So and then I will show you the proximal method, which does not require this adjustment here. Okay, but suppose for now we care about this algorithm ULA, which is biased. What kind of bias convergence guarantee can we say? So here's one example statement we can show. This was work with my colleague Santosh Vempala at Georgia Tech. So if your target satisfies log Sobolev, so think of this noisy distribution, and smooth. So the negative log density has bounded Hessian. Then along this algorithm with small enough step size, your KL divergence at the kth iterate is bounded by these two terms. The first term tends to 0 with iteration. So this looks like the continuous time exponential decay. But then you have this additional term which doesn't go to 0 with iteration. So this is the asymptotic bias. So this bias scales with step size, dimension, smoothness, and your log Sobolev constant. Right? And then if you want to extract number of iterations from this, one way you can do that is to say that if you want this upper bound to be less than epsilon, then to make this bias small, you're forced to choose step size to be on the order of epsilon, your target accuracy. And then you want to make the first part here small, so then you're forced to choose number of iteration to be on the order of 1 over step size. And then the end result will be something like this. Number of iterations is proportional to dimension, smoothness, condition number, and then there is this 1 over epsilon here. And this 1 over epsilon here is what we want to remove in this talk. Right? This is what's called low accuracy guarantee. If we have this polynomial dependence in 1 over epsilon, And this is not satisfactory from the theoretical perspective because in continuous time, we have exponential convergence. Really, we want logarithmic dependence. And from optimization for gradient descent, we know we can get logarithmic dependence, right? So somehow there is something wrong with this algorithm here. And then maybe let me just try to sketch very quickly why you can ask why is this algorithm biased? Like what's wrong with this algorithm, right? One way to view that this is not the correct algorithm is to say that in our view of sampling as minimizing KL divergence, let's write down the objective function as the sum of two terms: expectation of the log density, so this is my potential energy, plus this negative entropy. If we run the gradient flow dynamics to minimize these two terms, we get Langevin dynamics. But really, the first term here, this is coming from gradient flow to minimize the potential energy. And then the Brownian motion, the heat equation, is really the gradient flow to minimize entropy. Right? So in continuous time is fine because you're doing flow for both terms simultaneously. In discrete time, what is this algorithm doing? This ULA algorithm is doing first from xk. Let me take a gradient descent step for this f part. Turns out that is exactly the gradient descent algorithm on the space of distribution to minimize the first part, my potential energy. And then in the second part, I'm adding Gaussian noise. So I'm convolving with Gaussian. That's the result of the exact evolution of Brownian motion. So that is actually doing gradient flow to minimize my second component. So this algorithm ULA is actually doing what's called forward flow discretization of gradient flow dynamics. But for optimization, forward flow is biased in general. And really, we know that we want to run the forward-backward algorithm. Right? If in the first step we're doing a forward method, in the second step we should be doing the backward method, the proximal method, so that the overall algorithm is unbiased. Right? The issue with sampling is that the backward step for entropy is not implementable. Yes.
Does this flow have anything to do with the diffusion type of flow? Like, so some people talk about diffusion, diffusion as a kind of flow, like ODE flow. These two things are connected.
In a way, yes. You can write down the gradient flow dynamics for this one. Actually, not too related. Yeah, like if you once you have the PDE, you can realize that via either this stochastic process or this deterministic ODE. But this is operating at a step above that before we get what is even the right dynamics.
Flow distribution, like a Hawker class.
Yeah, but even before that, like so the true forward-backward algorithm, for example, for this decomposition, is that in the second step we really want to run the proximal method to minimize negative entropy. So the update would be that if we have some current iterate, say rho k plus 1/2, we want to find the next distribution to minimize this regularized objective function. But this is not. It's not a flow explicitly. Like I guess you can write down what is the interpolating flow, right? Yeah, but it's still operating at the level. What is the update you want to make?
If I'm not implementable, it would mean that the computational second step, that is.
Yeah, so for me, not implementable means that I want an update such that I can do that if I only have a sample from my distribution. Right? So in the first step, really I want I don't write it here. I want my update to be a push forward of this identity minus gradient.
All right, got it.
Yeah.
You never have a description of that distribution to begin with.
Yeah, I only have a sample, and then I don't know how to solve this exactly. Yes. But this was analyzed in a previous paper, and they showed that it has express convergence, except that you cannot implement this except in very special samples. Yeah. And then the advantage of Proximal Sampler is that it avoids that issue and it's actually implementable. And this one has a lot of connection to the diffusion model. Yeah. Okay. Are there any questions so far about this? Okay, so let me describe this new algorithm proximal sampler. And here's one description of the algorithm. So recall that I want to sample from e to negative f. Let me call that target new superscript x, because now I will look at this phase space. The first step would be, let me define a joint distribution on the phase space, so RD cross RD. And the density function of my joint distribution looks like exponential of negative f, my original target. And then let me add this quadratic component, x minus y squared, with some step size 1/2 eta. So for now, eta can be any positive step size. And one advantage or one property of this joint distribution is that if you marginalize over the y component, if you integrate over y, you get back exactly e to negative f. You get back your original x target. Right? So then the proposal will be, let's sample from this joint distribution, and then let me drop the y component and just return to you the x component. That will be a good sample from your target distribution. And then how do you sample from this joint distribution? This was proposed in a paper by Yinchat Lee and former students at this conference called a few years ago. What they proposed was, let's run keep sampling to sample from this joint distribution. So more precisely, this alternating keep sampling. So from my current iterate, say xk, let me draw my y component conditional on my current x from the correct conditional of this target of this joint target. Right? So if I condition on x, I want to look at the y given x conditional of this. Let's I drop the x component, and I get exactly Gaussian distribution. So the first part is easy. From my x is iterate, let me just add Gaussian with variance eta. So that's what this first step here, it's Gaussian. In the second step, from my y iterate, I want to draw x given y from the other conditional, x given y. And this is what they call the restricted Gaussian oracle. What this looks like is that in the second step, we want to draw a sample from this distribution over x, fixing y. Right? And another question is, how do you do this? Turns out one way to do that is via rejection sampling. And this is because I have a slide here that if my f, for now, if I assume that f is smooth on the second derivative, and if I choose my steps as eta to be small on the order of 1 over smoothness times dimension, then it turns out that this objective, this target distribution becomes strongly log-concave and smooth, and the condition number is a constant. And then I can do rejection sampling with Gaussian proposal, and I can control the number of iteration. In expectation will be a constant in each iteration. You have a question? And yeah, so in that sense, we can implement this, and then I want to focus on assuming that we can implement the second step. What can we say about the mixing time, the convergence guarantee of this outer iteration, right? Because this, and I have a slide here in detail if people are interested, because this is saying that in each outer iteration, I can spend a constant number of computation to actually sample from this exactly.
So this is the main point that this function over here becomes strongly log-concave. So you have more control on them.
Yeah. Yeah, sorry, I thought I had it in the appendix, but yeah, but exactly. So so if my f is smooth, then this regularized function becomes strongly convex and smooth with this condition number. And then there is this general fact that for any strongly log-concave and smooth target, you can use rejection sampling with Gaussian proposal. The Gaussian proposal means that in every iteration, you want to find the minimizer of this objective. Use Gaussian centered at that minimizer, and then you can bound the number of trials until success, and it scales with condition number to dimension. So in this case, this is the condition number. So then here's what we say that if you choose the step size to be small on the order of 1 over smoothness times dimension, then this expected number of queries becomes this quantity, which is a constant over dimension. Yeah. But in principle, you can use any other things you want to sample from this. Rejection sampling is good because it gives you exact sample with a randomized number of trials. If you use something else to sample from this one, if you use an approximate sampler, then you have an error, and that error you need to control how it propagates. Yeah, but in this talk, I'm assuming that we use rejection sampling, so we get an exact sample from this target, and then I care about what is the mixing time of this outer iteration. Okay, so what kind of guarantees can we show about this algorithm? So this is what the original paper showed in 2021. So they studied the strongly log-concave setting. In continuous time, we get exponential convergence in distance to minimizer. In discrete time, they show that the algorithm, this is the outer iteration, also has this exponential convergence in distance. But with this, instead of exponential, it becomes this 1/1 plus strong log-concavity constant times step size to the power of iteration. And if you look at this really matches what we know from optimization. In optimization, if we minimize strongly convex function, we get this exponential convergence in distance. And then in discrete time, the proximal point method also has an exponential convergence, but in this form. That really matches what we have here, or what they show. So this was what they showed in 2021. And then in the following year, with some colleagues, we showed that turns out that the same algorithm, we give a different analysis under weaker condition. So under log-Sobolev, for example, we know that in continuous time, we get exponential rate in KL divergence. In discrete time, we can also show that we get this exponential convergence in KL divergence here. Again, with the same form of convergence rate here. And then if we take this one, for example, then we can extract, so this is the same statement. Then we can extract the number of iterations to get error epsilon in KL divergence using this algorithm. Also, this theorem above here, this holds for any step size eta. And then we say that really, in reality, we need to choose step size eta to be small, only 1/, smoothness times dimension. So therefore, the number of iterations to reach error epsilon scales with there is dimension, condition number, and log 1/epsilon. And so this matches the logarithmic part matches continuous time, also matches what we expect from optimization, except that for sampling, we get this additional factor of dimension here. And compare this with the unadjusted Langevin that has this polynomial dependence in 1/epsilon here. So this was for KL divergence, and then let me just flash you through a few more results saying that turns out that for Renyi divergence, we can also match this in discrete time. The optimization meaning is still not as clear because log-Sobolev is the PL condition for KL divergence, but turns out that we can get guarantees even in Renyi divergence. And then in Fisher information, in Fisher information, under strong log-concavity now, in continuous time, we have exponential rate in Fisher information. We can show that in discrete time, we also get similar, the same rate. And again, this matches what we expect from optimization. If we minimize strongly convex objective function, we get exponential convergence in squared gradient norm, both in continuous time and in discrete time. Yeah, and then in the paper, you can also say convergence on the point carry under weaker isoperimetry. Okay, let me skip this part and okay, and I can say a few words about the proof technique using what's called data processing inequality. But let me pause here for a second, see if there are questions. Yes.
Before you still have the explanation, kind of conversion, well, not explanation, whatever.
So if you have point carry, what you can show is that in continuous time, the Ragni divergence will decrease at a rate that's initially linear in t, and then eventually exponential. And in discrete time, it has the same matching, right? That initially decreasing linearly with iteration, and then once it hits below a constant, say below 1, it decreases exponentially fast. Yeah.
But the proof still use some kind of strong log-concavity.
No, the proof here.
When we're not showing.
The proof technique has to do with in continuous time you differentiate the time derivative of Ragni divergence along Langevin. You get some negative Ragni visual information, and then Poincare inequality. You can using Poincare you can show that you can bound the dissipation as a function of Ragni divergence.
No, but that's for the larger part, but for proximal sampler, do you need to change?
Yeah. Let me show you the proof then. The proof technique turns out to be the same as continuous time. So does someone else have a question? Okay, let me show you the one word about the proof technique. So broadly speaking, what we do is establishing data processing for these various algorithms. So in information theory, data processing says that if we have any noisy channel, any noisy process, if we have any two input distributions, then the output will be closer together. They can never get farther apart. And this holds if you measure the distance, how far away they are, in anything involving say phi divergence, including Ragni divergence, KL, TV distance, and so on. So in general, there is just this weak inequality here, but strong data processing inequality says that for some channels and for some distribution, you can have strict inequality. So this ratio can be less than 1. And yeah, and then this is like one general technique for proving. So let me parse this. So turns out that for a lot of algorithms, for a lot of problems, what this channel looks like is that this is the result of some evolution of a stochastic process with some PDE from input to output. And a general class of PDE is what's called it's just this Fokker-Planck equation, where the evolution of your density is some divergence term with some drift term, plus some diffusion component. And then there is this general fact that just by computation, you can show that if you have two distributions, rho t and nu t, both of them evolve following the same PDE with the same drift term and the same diffusion component here, then you can compute the time derivative of KL divergence and you get negative visual information. And then we can change this with the fact that if we know that the second distribution satisfies log life, for example, then we can change this here, and then we can integrate and get this exponential convergence rate. And what it says is that if your channel is the output of this PDE, then you get a strong data processing inequality where this is your constant, how much it decays. So I'm writing it for for KL divergence, but you can do the same calculation, and it holds for Ragni divergence, for phi divergence, for chi-squared, and so on, right? And then what we do is we specialize this for a lot of the different channels. So for proximal sampler, before that, even for continuous time Langevin, right? For Langevin dynamics, what we do is that we set the second distribution ut to be the stationary distribution, and then this recovers the classical the Bruin's identity. But for us, for this discrete time algorithm, what we do is the following. Suppose that I look at the first step, adding this Gaussian noise. I run that from my current iterate xk to get say yk. Right? So xk has distribution rho kx. And then yk has some distribution rho ky, just rho kx convolved with Gaussian. Now imagine doing the same step, adding Gaussian, but starting from my stationary distribution target. Then I go to something else, new y, which is just convolution with Gaussian. The claim is that even in the first step here, this forward step already contracts my KL divergence. But now on the right-hand side, this is the KL divergence of my current iterate. on the in the output, I get KL between my y iterate and my not my target new x, but my y target. But the contraction rate has to do with this 1/1 plus log Sobolev constant and step size. Eta is how much Gaussian noise you have. And how do you show something like this? We interpret this Gaussian noise as the result of this Gaussian channel as the output of the Brownian motion, or really the output of this heat equation at time eta. And then what it says is that I have two distributions, both of them evolving via the same equation, the heat equation. And then I apply this identity here, and then I just need to control my log Sobolev constant. And then here's where we say that if I know that my target has log Sobolev, I can control what is my log Sobolev evolution along this Gaussian channel. And then when I integrate that, that gives me exactly this factor here, 1/1 plus of eta. So the same proof holds also for Ragni divergence, for chi-squared, and so on. And also under Poincare inequality. And then in the second step, for this backward step, really in the backward step, we can just say that just by weak data processing, we never increase the output. But as a result, we can extract something stronger than that. Turns out that in the backward step, we also get a symmetric contraction here. And I won't get into the detail, but one way to show this is to say that in the backward step, we sample from this RGO, this conditional distribution. And it turns out that this conditional distribution, x given y, it is exactly the output of some stochastic process. And what this stochastic process is, this is just the time reversal of the heat equation. So in the forward step, in the previous slide, I have my forward process is a Brownian motion. And then if we do the same principle as diffusion model, that you end up here, you define the time reversal, and you define the stochastic process that interpolates that. That gives you exactly this SDE. So it turns out that the output of this backward process is exactly the RGO that we want. And then once we have this, then we are good because because then we can do the same calculation that we have two distributions, both of them evolving via the same channel, and then we can do the time derivative computation, and then that's what gives us this. Yeah, but I think it's really interesting that this work we did this work a few years ago, at least before I knew anything about diffusion model. We came up with this proof just from analyzing this. But really, this is the same principle as diffusion model. The difference is that for proximal sampler, we run this forward and backward process for short time step eta. That has to do 1/, smoothness times dimension. And in the backward step, this is just a proof technique. But the way we implement the backward step is really via rejection sampling. Whereas for diffusion model, typically we push forward via some process for a long time until we end up at some, say, Gaussian. And then we simulate the backward process also for a long time, right? And the way that in diffusion model, the way we simulate the backward process is via discretizing this SDE and via approximating the score function. Here we don't need any of that because for us, the backward step is happening only for short time. So we can do rejection sampling instead. Yeah, but the proof technique is, this is appearing just in the proof technique. Yeah, and then if we change those two steps, right? In the first step for the Gaussian part, we move from the x to the y, we get some contraction. In the second step, we move from y to x, we get some contraction. So then when we combine that in each iteration, forward and backward, we go from the x iterate to the next x iterate, and then we pick up this contraction factor. And the same thing for Ragni divergence. Okay, I think I'm almost out of time. Maybe let me skip this part. There is one question: how do you show this in feature information? Because feature information is not a phi divergence, so none of this data processing applies. Turns out that for feature information, it's not even true that weak data processing holds. Turns out you can construct examples where you add noise and your feature information can increase. So this is just a specific example. But then turns out what's nice is that you can show data processing and feature information under some assumption, under log-concavity or under strong log-concavity, for example. And then this is what we use to extract this convergence guarantee in proximal sampler. The proof is really the same, just deriving a more complicated formula, but yeah, it's just computation. Okay, so let me just summarize by saying that yeah, so in this work I tried to present some results about this sampling from this perspective of optimization in the space of distributions, and I think this has been a fruitful, hopefully useful perspective because it tells us, at least it tells me, what kind of guarantee can we expect to get. Like for example, for the forward method, we did not get the correct unbiased rate, so then. That's what motivated us to really look into this proximal sampler. And more specifically, here we showed that yeah, Langevin dynamics gradient flow. Proximal sampler is some approximate version of proximal gradient method. In the paper, we have a more specific, more explicit correspondence. It has unbiased convergence guarantees, matching continuous time, matching optimization. And I think what's interesting is that in the proof technique, turns out that a lot of what we've done, a lot of what some people have done in this community can be framed as just proving different data processing inequalities for all these different channels and different algorithms. Yeah, okay, I think that's the end. Thanks everyone. Happy to answer more questions.